In this, the final, mostly metaphysical part of the trilogy, I'll explain the nature of the Big Bang, why the matter-antimatter imbalance never annihilated one another, and why this interpretation of the Big Bang itself can adhere to the principles of sufficient reason. In the last part, we travel all the way back to the cosmic microwave background, and you would be in an infinite ball of primordial plasma, and for every second today 36 minutes would pass. You would not see a second hand going around 36 times a second. It would appear normal, like this one. We will now go back and look at what we now see as the cosmic microwave background. What we saw as the surface of last scattering is now the infinite ball of primordial plasma to which we would be in the middle. Go back to this particle horizon, and clock time tends to infinitely fast. This makes the Big Bang a continuum from which we emerged when relative time began to slow at t equals 0. In Sir Roger Penrose's conformal cyclic cosmology model, the universe cycles from Big Bang to Big Bang. Each cosmic iteration he calls an aeon of time. Time has no meaning for a photon, making the early radiation epoch timeless at the beginning of the aeon, and again at the end, when all black holes have evaporated into Hawking radiation. He concludes that the model can be considered dimensionally conformal, as he points out in his lecture on Seeing Through the Big Bang into Another World. This is also true of my scalar model with isomorphic transformations, so it is also a conformal cyclic cosmology model, so I also use the same phrase, aeon of time. To simplify my model graphically, I will start by representing space like this, and the primordial matter from the perspective of a test particle with its Hubble sphere by this shrinking blue ball. Our aeon of time starts when we emerge from the Big Bang, when the fastest clock time provides the longest duration. I represented here with these two arrows, one for the absolute displacement and one for the relative duration. At the Big Bang, we have an infinitesimal displacement with an infinite duration, from which our transfinite aeon of time emerges. This red rectangle represents this early infinite ball of primordial plasma stage that we see here in the background. At the other end of the aeon of time, we have an infinite time displacement and an infinitesimal duration. All matter will have collapsed, along with the Hubble sphere, and with no future horizon of causality within our aeon of time, Hawking radiation evaporates all matter into the next radiation stage that emerges from the Big Bang continuum at t equals 0 of the next cyclic iteration. This model distinguishes between absolute space and the fields of Faraday's space-filling lines of force that permeate space, so that when the primordial plasma condensed into molecular hydrogen, the coordinate speed of light and the Hubble sphere was far greater than today. Because the gravitational constant is inversely proportionate to the Hubble sphere, the effect makes gravity weaker in the past, but with a far greater absolute range. The primordial gas clouds could therefore have an upper limit larger than the largest structures that we observe today. Further shrinkage of the Hubble sphere increases the strength of gravity and breaks up the clouds until the conditions are right to form quasars at the center of galaxy-sized clouds. Gravity is still much weaker than today, and it took far more matter to reach the Chandrasekhar mass required to form the quasars. The ejected material seeds the neighboring clouds to produce the first stars. Galaxies continued to shrink and merge to evolve what we see today. Eventually, the cosmic background radiation cools beyond detection, and all matter collapses under gravity, where the lack of relative time duration makes the Hawking radiation the genesis of the next Big Bang. Our aeon of time emerges from the Big Bang, and as it evolves, it loops back to the Big Bang, an interface where a phase transition takes place. It is a timeless continuum that has always existed. There are infinitely many aeons of time, each beyond the horizon of causality of their older and younger counterparts. But so far, I have only described a matter-dominated universe. And if this represents the matter field, then antimatter should also emerge from the Big Bang. Matter and antimatter doppelganger aeons emerge simultaneously yet cannot react with each other as they are immediately beyond one another's horizon of causality. We should, however, think of this as being three-dimensional, spatially and temporally, and is better described by this horn torus gif. Imagine our aeon of time being fractionalised into infinitely many transfinite doppelgangers, all beyond one another's horizon of causality. If we are in this aeon, then this one would be its antimatter twin, and the same with these, or this one and this one. Summing up, the electromagnetic arrow of time means that light always travels from the past to the present. There is also a cosmological arrow of time, as the universe evolves throughout our aeon. The speed of light is constant at any now moment, but our light speed rulers are shrinking over absolute time. We age and experience time as a duration, so that relative time is another time dimension, depicting how fast you're travelling through absolute time in the present. Like a speedo in your car lets you know your instantaneous rate of change, so too does the Hubble parameter. Faster clocks produce a slower Hubble constant, and slower clocks in a gravity well produce a faster Hubble constant. And a simple idea may explain how to resolve dark energy. Our shrinking rulers produce a fictitious movement that naturally speeds up, but represents no inertial movement or absolute positional change. Therefore, no energy is needed to invoke it. Dark matter. Orbital speeds are relative to the clock of the orbital inertial reference frame. The relative clock time of the outer stars in this galaxy will be ticking faster, so their emergent orbital speed is slower than stars that are deeper in the gravity well, even though they appear almost synchronous. Horizon problem. In this model, the Hubble sphere is at Z1 and 14 billion light years away. Our visible horizon is a cosmic microwave background at nearly Z11,000. Therefore, the universe was either 11,000 times older in relative time, but not in absolute time, or the speed of light was 11,000 times faster in absolute time, yet still at the constant c in relative time, that is, when the light left the cosmic microwave background. Even an infinite particle horizon could have been in thermal equilibrium at our Big Bang moment. Although the colours here represent temperature variations, there is only a 10,000th of a degree Kelvin difference between the hottest and the coldest. Flatness or oldness problem. In the Big Bang model, there are three ways that the universe can evolve depending on the relative density, omega naught. Too high, when omega is greater than 1, and the universe expansion slows down and recollapses into the Big Crunch. Just right, when omega naught equals 1, and the universe expands forever. And this is what the data is telling us. If this is the case, it is quite remarkable after all this time. The fine-tuning for this to be so has been compared to balancing a pencil on its point at the beginning of time, and it's still standing there now. If it is too low, then the universe is open and we head for the big freeze with no end. Parallel lines diverge in a strange hyperbolic space geometry. As matter shrinks with our light speed rulers, absolute space appears to expand. Space is flat on the large scale and over time. Matter gets no inertial movement from the apparent expansion, so the pencil analogy would be that it is dangling from a thread, and very stable indeed. This is how current theories see the evolutionary age of the universe. The cosmological principle assumes that the universe is homogeneous and isotropic viewed from a large enough scale. And so everything here looks the same with accelerated expansion. Or the universe looks younger, less developed here. Things start to become visible here, and everything is in the process of cosmic inflation here. But the expansion over time does not adhere to the cosmological principle. If it did, this graph would look more like this. So when we look at the expansion as a changing distance scale with space remaining absolute, even the time narrative of the universe becomes homogeneous and isotropic. This model adheres to what cosmologists call a perfect cosmological principle. The Hubble tension. The combined time dilation of special and general relativity means the Hubble Space Telescope is travelling faster through absolute time than the WMAP satellite. The Hubble constant is an indication of just how fast. Matter-antimatter imbalance. They never annihilated one another, they just separated at the aeons genesis moment and beyond one another's horizon of causality, hidden by the cosmic microwave background. The Big Bang itself can adhere to the principle of the sufficient reason. Features of this model. It is infinite, it's flat, it's a conformal cyclic cosmology, scalar and static, it has relative apparent expansion, has only one parameter, and is holistically a steady state. It matches observations. This model is metaphysically logical. Thank you for following me down the rabbit hole of cosmology.